Hi, everyone. So today we are talking about calculus, potential energy, and what's called the CoE Bonanza. They're massive problems that we're going to solve in a little bit. But first, we are going to talk about calculus. Okay, so what is the calculus used to derive f of x from a u of x function? Well, first, we know a couple things. First, we know that u of x, okay, equals, this is actually the negative integral of f dr. Okay, we never did this in class, but where work is the integral of f dr, potential energy is technically the negative integral of f dr. Okay, this is really more because that negative kind of shows that potential energy is equal to the force it takes to resist gravity, right? Gravity's pulling you down, it takes force to resist it, right? So when I give this pencil potential energy, what I'm doing is I'm giving it the energy it takes to resist gravity, right? Or when you compress a spring, I'm exerting, that spring has the potential to resist your force, but it isn't, right? So it's all about the resistance. So that's why this negative is here, right? But anyway, so the potential energy is the integral of force. That must mean that force is the derivative of work over distance, or the derivative of energy over distance. Okay, so we're looking at derivatives. Now, if we want to look at, so that's the answer to A, right? What is the calculus? That is a derivative. That's your answer for that. Now for part B, it asks us to sketch the curve of f of x versus x from 0 to 9.5 meters up to that letter E, and label points A through E. So what we're looking at here is a complex parabola. Okay, we have concave down, right? Concave down for this point. Okay, but then it turns to concave up, and then back to concave down. Okay? So we've got these two inflection points. I'm going to fudge the numbers and just put those at 0 energy. So wherever that hits, that we're going to say that's 2.5 and 7. So let's put some hash marks: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at, what is that, 2.5 and 7, those will be our inflection points. Now, if you remember from math class, an inflection point, when you take the derivative of that point, that's actually going to show a sharp point on a derivative graph. But if we want to see where the slope is 0, where we'll have 0, we'll say that A is kind of at 0. It looks like it was very close to 0. C is at 0, and E also at 0. So we'll start at A. A we'll say is at 0. Okay, then what are our Y values? It goes up to 4 and down to -4. So we'll have a 1, 2, 3, 4. 1, 2, 3, 4. Going by ones, we go to 4 and 10. So A we'll say is at 0, as at a position 0. Now at B, we can see that slope gets more and more negative up until our inflection point. So B, it looks like it's almost just -1, right? You've got, actually that would be -1, -2, right? It's down 2 over 1, so it's almost a -2. So we would say that whatever B is at 1.5, we're down to -2, abouts. Right? Then we have our inflection point at 2.5. So that is going to be somewhere around here. And then C at around 5. What's that? 2, 3, 4, 5. C would be right here. So if this is B, that would be C. So our graph looks something like this. Okay. I'm going to be off a little bit. I'm sorry. Not a great artist here, but that's about what we're going to look at there. Now, from C to some inflection point D, we will spike, and then D is shortly after the inflection point, around about 8. Okay, so about 8, we have a positive slope. Let's say that's about there. What could we estimate D to be? Let's see, we've got that's right there, that's right there. So it looks like it's rising by about 1.5. Okay, so we'll call that 1.5. So D would be 1.5 at distance about 8. So we would have something around here for point D. And then E, we're going to return to 0 right there. So this is going to look a little funky. I'm going to move that. The issue really is that my hash marks are not very good on my x-axis and y-axis. But that is something that we're going, right? So that's our A, B, C, D, and here we're ending right there at E. So that's what a derivative of this kind of graph can look like. Okay, we are looking at the slope throughout the entire thing. And there is a sharp point at the inflection point because it is going negative and then it suddenly turns positive. Okay, there is no smoothness about that. It's just boop, goes from moving positive to moving negative to moving positive, or moving positive to suddenly moving negative. So common to have those kind of points on your derivative graphs. So that's the curve for force versus distance if we start with an energy graph. So that's how we can do that kind of calculus, right? Using calculus to graph it. Now let's use calculus to actually get a function. We can also use multivariable calculus on this. So this will give us some practice here. Now remember, if u is the negative integral of f dr, that means that f is the negative derivative with respect to x, right? Or I guess that would be more accurately with respect to r. So here we will actually put that negative into use. Before we were just finding the derivative. Now we will actually use that. So here we have a u function of 2x squared y cubed minus 8y. And what we want to do is we want to find the equation for force acting on the particle at any point xy. That's the important key here. Now what you're going to do is you're going to take the partial derivative to get a 2-component unit vector for force. So how this will work is we will have the negative derivative of energy with respect to x, and that will be our I hat of the vector. Then you'll have du dy, and that will be the j hat of your vector, and that will all be in newtons. So let's find these two derivatives. So if we went du dx, okay, what we're doing is we're essentially taking, this would be, we can rewrite this as 2y cubed times x squared minus 8y. Okay? And this is a constant and this is a constant. So remember, when you take the derivative of a constant, that goes to 0. And when you have a constant times your variable, that's when you just use the power rule. So you bring your 2 down, you've got 4y cubed x. And that's it, because then that goes to 0. So that's our du dx. Next, if we wanted du dy, what we would do is, I'm going to rewrite this in a different way. You could say that this is 2x squared times y cubed, constant there, minus 8y. 8 is our constant. So let's say we take the derivative of that, bring your 3 down. You've got 6x squared, y squared, minus, now if we take the derivative of this, You'd imagine there's a 1 there, so bring your 1 down. 8 times 1 is 8. Then subtract 1 from that. Y to the 0 is 1. 8 times 1 is 8. So that's our derivative of those two, but now we need to plug them in to get a force equation. So we have negative 4xy cubed I hat minus 6x squared y squared minus 8 j hat, and that is all in newtons. So you just take the derivative separately, but you take the derivative with one variable, and then you take the derivative with respect to another variable, and then you plug that into a vector with respect to I and j. And now remember, x corresponds to I, y corresponds to j. That's why those are lining up like that. Right? That's why they correspond. So that's how we can use calculus to get an equation. Up above is using calculus to find a graph. Now we've got two problems, the CoE Bonanza and then the CoE Palooza. So we have this block. A block is released from point A, and the track is frictionless, except for between points B and C. You can see it's jagged through there, right? Now, part A asks, write an equation to solve for the coefficient of friction for the friction between B and C, but we want that with respect to the block's mass, gravity, spring constant K, and maximum spring compression distance from equilibrium. So this is very specific what they want. So to do this, we need to set up our CoE strategically. First, we need our initial energy. Okay? If we don't include A, there's basically no energy in it, right? We can't find our kinetic energy without the gravitational energy. So we would say that we start with UG naught, K naught, but that's going to go to rest, right? And then you've got the starting spring potential, which is sitting at its equilibrium, so that'd be ZPL. Okay? Now, to figure out what we want to do for our final scenario, right? We've got our initial. Finally, we can't use B, right? Because that doesn't even include the spring constant or the spring compression. We can't use C because that doesn't include the spring constant or spring compression. So we have to use new point D. This is going to be the maximum spring compression. So we have UGF plus KF plus USF plus work taken away by friction. However, at point D, we can say that is our gravitational ZPL, so that goes to 0. If it's the maximum compression, it is going to be at rest. So we just have the energy from the spring and the work of friction. So what this equation shows us is that our gravitational potential energy gets converted to kinetic as it slides down. But that kinetic energy loses some energy to friction. Okay? That's accounted for by our work of friction. So it's going to lose some energy through here. Right here, it's going to lose some energy. That's accounted by our work of friction, right? And then the rest of the kinetic energy goes directly into the spring to compress it. So as that potential energy converts to kinetic, we can see where all of that kinetic energy goes. It goes into the spring, and some is lost due to friction. So this is actually an accurate account of what's happening just with those three energies. Now, it asked us for an equation to solve for the coefficient of friction. So we want mu. Mu is the goal. And we need it in terms of mass, gravity, spring constant, and the maximum compression distance, and nothing else. So let's work through this. We have mgh equals 1/2 kx squared plus mu nd. Okay. As we are sliding along from points B to C, N will equal mg. You can draw a free body diagram. There's no other forces acting other than mg normal and force of friction. So normal equals mg. And let's see, what else is illegal? H is illegal and D is illegal. Well, we actually have values for that. H is 3 and D is 6. H equals 3, D equals 6. So we can actually just plug those in and we can solve for mu. We have 3mg equals 1/2 kx squared plus mu mg times 6. So I'll move that 6 when I do my math. So let's solve for mu. Mu, you take that 3mg minus 1/2 kx squared, then you divide by 6mg, and that will give you mu. So that's our equation in the terms that they want. M, G, K, and X. We can see that those are the only variables that we have in the problem. Good. Now, let's see what else it asks. Part B, beyond givens shown in the diagram, we have the height and the distance. What would the experimenter have to measure to find a numerical answer? So that they would have to measure mass. We know gravity. They would have to measure the spring constant K and the distance the spring is compressed. And letter C appears to give us M, K, and X. So we can actually solve this. So what if M equals 10? I'll write that down here. M equals 10 kilograms. K equals 2,250 newtons per meter. That's kilonewtons up there. And then X is 30 centimeters, so X would equal 0.3 meters. So if we plug this in, our mu would equal 3 times 10 times 9.81. Then you subtract 1/2 times 2,250 times 0.3 squared, all divided by 6 times 10 times 9.81. Okay. And if you put that into your calculators, you get something very close to 0.328. Okay. So this is they actually bring in the experimenter, which is not something that we talk about much in these problems, but this is actually a valid experiment. If we could account for, say, if we stretched B all the way out to here and C all the way out to here, then we could actually see if that gravitational potential, hopefully it converts most of its energy to kinetic, right? It's going to be hard to make that ramp frictionless and to measure any friction on that ramp. So that would be tough. But we have from A to B, then the friction from B to C. Then if that spring, we just measure how far it compresses, we'd be able to figure that out. Finding the mass of a block is not difficult. When you buy a spring, like a scientific spring, you know the K. It comes with that information. Sometimes you actually buy it in terms of K, like you want a 5 Newton per meter spring or a 50 or a 75 Newton per meter spring. So you would already know your mass, your K. Finding X, just do that Mythbuster style, use slow motion camera with a ruler behind it to see how much it compresses. Then repeat to get some good data, and you could actually do that experiment. So that one is really cool. Now this experiment you definitely could do. It would just be a real pain in the butt. This is a really hard problem. So we have a pendulum comprising a light string swings in a vertical plane as shown. Okay? Show that if the pendulum is released from rest at the horizontal position, okay, that is out here, right? That is our starting position. If it starts out there and is to swing a complete circle around our peg. So look, it's going to come down here, and then it will convert all of its potential energy to kinetic down here. Then it's going to encounter this peg. That peg right there is going to cause it to spin with a new radius. Instead of length L, it will have a new radius. If it's going to swing a complete circle around the peg, the minimum value of D must be 3L divided by 5. And we must show that that is true. So this is going to be tough. So let's look what we want to do here. We're going to start at our starting position, right, at that horizontal position. Theta equals 90 because theta is relative to the vertical. So we have UG naught plus K naught. It's going to equal 0 for rest. Okay, it's just sitting at rest. So then our final position is actually going to be wherever the top position is here as it swings around. So we would say this is UG top plus K final. No springs, no friction. That's all we're dealing with, right? Now we want to find the minimum value of D. So let's set our initial value equal to the ZPL. And then we have 0 equals UG top plus final kinetic energy. Okay. So this is going to get hairy. We're going to have to find two specific variables. So let's write this out. We have 0 equals mgh plus 1/2 mv final squared. Okay. Now, a couple of things we don't have. Okay, we obviously don't have the mass. That's good. We can't really solve for that. But what we'll need to solve for, we'll need to get something for h. We'll need to get something for v squared. So let's start with h first. Okay, if I'm going to redo this diagram a little bit so I can use it. So h, okay, h is this. If this were to continue, let's say that this right here, that is h. Okay, so we want to find that h. Well, we first need to narrow things down, right? Let's get a couple equations here. So we've got the radius here, radius r, that equals L minus D. We've done that in problems before, right? You take the entire length L, subtract out length D, and all you're left with is radius R. Okay? So we know that. Let's see, so if we want height H, if we took L, we can't do L minus D or L minus R. If we did L minus 2R, that could work. So let's say that we have H equals L minus 2, L minus D. Okay. So yeah, as that comes up, right, we want to subtract the entire diameter of the circle from our length. The diameter is 2R. So that means our H is L minus 2L plus 2D. So H would be 2D minus L. And we need that specifically in terms of L and D because you can see D is in terms of L, not in terms of R. So we need to make sure that the R is completely gotten rid of, right? So we know H. Let's put that in here, right? We have 0 equals mg times 2D minus L plus 1/2 mv final squared. Now, if you'll remember back a couple of videos ago when we did centripetal motion and energy, if you hit a brick wall right here and you're missing a v squared in a centripetal motion problem. Now remember, we are going in a circle. Where you can get the v squared, you can actually go back to summation of forces. Okay, so you can actually go we could actually just use acceleration to find that, right? If we say AC is v squared over r, this is going to incorporate an r, but we can, we have an equation for r, so that's not an issue. We can get rid of r. What is our acceleration here? Well, our acceleration is really just g, right? We need enough kinetic energy to have centripetal acceleration of at least g. If not, then the pendulum's just going to fall, and then it doesn't actually complete its circle, right? So if we say this equals g, then v squared equals gr, which is something we've come up often, right? In our problems. How many times have you seen v equals square root gr, right? We come up with that pretty often. So we'll say v squared is gr because we need to have that centripetal acceleration of at least g just to make it up to the top, right? So it needs to be at least g, because we're just figuring out if it's enough to swing the complete circle, right? So we'll put gr in for that. So we have square root of 0 equals mg times 2d minus L plus 1/2 mgr. Okay, and we actually have r. R is L minus d. So let's go ahead and plug that in. We have, actually, you know what? Let's go ahead and subtract that over. So we have a, so we're going to incorporate a negative. So this is going to get complicated. What we can do here is say that our height is negative, okay, which it is, right? It is below the ZPL. So let's add that over, because we can say that this is actually a negative mg 2d minus L. So let's add that over to solve for this. So we've got mg times 2d minus L equals 1/2 mg times r, which is what, L minus d? L minus d, there we go. Okay, so here we're going to solve for d. Right out of the gate, m's can go away. G can also go away. So if we're just solving for the distance d, we already have 2d minus L equals, what is that? I guess it'd be L over 2 minus d over 2. So now let's just solve for the distance d. Let's multiply everything by 2. So you have, oh goodness, lagging on me a little bit. Zoom in. We have 4d minus 2L equals L minus d. Let's add that d over. So we'll do plus d. We will add 2L to everything. So that goes away, that goes away. So we've got 5d equals 3L. Holy smokes, wouldn't you know, d equals 3L over 5. Bingo, bango, we were able to show it. Now the hard parts here were h, okay? H. I unnecessarily made that negative complicated. That's something that we could have seen right out of the gate. For that h, okay, we've actually done this in another problem before. When you have 0 equals ug plus k, you can actually see that when you subtract that negative ug equals k, well, that ug is also going to have a negative h inside of it. So you can see that that's delta u equals delta k. We've done that before. So you don't actually have to regard that negative. You can also say that, let's do this. You can also see that that is 0 equals mg times negative h. So when you add it over, the negative goes away, right, to equal k. So that was my goof. I should have done that earlier in the problem. But our complications there were the h and the v final squared, which we were able to get easily just from centripetal acceleration to make it around that circle. All right, so those were two complex conservation of energy problems to end the chapter. This is the end of Chapter 8, Conservation of Energy, and we will continue on to Chapter 9 next time.